So the first one that we want to look at is page 3 of your worksheet. Here, they mention that the Earth may be considered to be a uniform sphere of radius 6.37 times 10 power 3 kilometer with its mass of 5.98 times 10 power 24 kg concentrated at its center. The Earth spins on its axis with a period of 24 hours. So in part 1, they tell you that there's a stone of mass 2.5 kg that rests on the Earth's surface at the equator. From there, calculate using Newton's law of gravitation, the gravitational force on the stone. So when they're asking you to calculate using Newton's law of gravitation, that is actually referring to this equation here. Okay, so what they mention is that you have Earth. Let's consider this sphere here as your Earth. And you have a small stone of mass 2.5 kg resting on the Earth's surface at the equator. So you consider now that you have a small stone right over here that's resting on the surface at the equator itself, like this. Let's just say that this one represents your equator. Okay, they want to find out what is the gravitational force acting on this 2.5 kg stone. The gravitational force acting on the stone is directed towards the center of the Earth. So you want to use Newton's law of gravitation. The equation is Fg equals to gmm over r squared. The big G is your value that you can get from your data sheet. Your big M and small m, which is the mass of the Earth and the mass of the stone respectively, you also know. Then you divide it by your separation square. Your separation is really just the radius of the Earth because your object is resting on the surface. Okay, so the separation between your two masses is really just the radius of the Earth itself. So let me just try and draw it out. Your R is really just the radius of the Earth. So here is in kilometer. You need to remember to change it back from kilometer to meter. That's the reason why you have 10 power 3 here. And don't forget to square. Eventually, you'll be able to get the answer as 24.6 Newton. Okay, so this is the gravitational force acting on the mass right now, determined using Newton's law of gravitation. Now in 2, they want you to then find out the force required to maintain the stone in its circular path. So what you do understand from here is that your Earth will tend to spin about its own axis with a period of 24 hours. Okay, so because the stone is resting on the surface of the Earth, it will move along with the Earth as it rotates about. So this stone here, you can imagine is actually moving in a circular motion like this. All right, there is circular motion, therefore there's supposed to be centripetal force. So when it comes to centripetal force, you can either use Fc equals to mv squared over r or Fc equals to mr omega squared. In your case, it may be easier just to use mr omega squared because eventually the omega can be substituted as something else where you say that omega is actually 2 pi over t. Right, because you are given the value for the period here, so it might be useful for you just to use omega being 2 pi over t to make your calculation simpler. So from there, just sub in the relevant quantities, right? Your mass is 2.5, your distance, remember to change it from kilometer to meter, and then your period, you remember to change it from 10 hours to minutes to seconds, so you have to multiply with 62 times. And don't forget to square. Eventually, you will get your answer as 0.0842 Newton. Okay, so the first one that you found above was the gravitational force. The second one that you found here is actually your centripetal force. Okay. Okay, then after that, the next part is where you kind of need to relate whatever you found. In your question now, in part 2, the stone is now hung from a Newton meter. So use your answer in 1, the ones that you've just found above here, to determine the reading on your meter, and then give your answers to 3 significant figures. And this question here is worth 2 marks. All right. So if you thought that the Newton meter is actually measuring the weight of the object, therefore you say that the reading is supposed to be 24.6 Newton, which is the answer above here, this one will be wrong, okay? Because your Newton meter isn't really measuring your weight, but rather your total downward force. So what I mean by that, you just consider this example here. If I give you a Newton meter right over here, let's just say that this is my Newton meter. I try to hang the Newton meter somewhere from a support. My Newton meter looks something like this with a square and a spring inside somewhere. All right, then this is where I hang my load. Okay. Say for example, right now, I tell you that the weight of my mass is 10 Newton. My Newton meter will tell me 10 Newton. Okay, this one here is my Newton meter. Okay, my Newton meter, this one is one example here. If I attach a weight of 10 Newton, the Newton meter will actually give me a reading of 10 Newton. But say for example, right now, I have that same Newton meter, and then I again have that same weight that is 10 Newton. What if this time I purposely apply another force on the weight? Maybe I use my hand and then try to pull the weight down even further. See, right now I apply another force of 20 Newton from your hand, from my hand, for example. I apply a 20 Newton force from my hand onto the weight here. What do you suppose would be your Newton meter reading? Your Newton meter reading here will now suddenly be 30 Newton, because it will be registering not only the weight of the object that you hung onto it, but also the force that you applied separately onto the weight itself. So here, when it comes to your Newton meter, it isn't really just measuring your weight. It is more accurate to say that it measures your resultant downward force. Okay, that is what your Newton meter actually does. It measures weight, that's correct, that's partly true. That is only if the force involved is just the weight. But if let's just say there are other forces involved, it really is measuring the total resultant force, not just the weight. So here, based on your understanding here, how do you do part 2 here? You have to consider the fact that you have gravitational force found here, and then after that you have centripetal force found after that. So think about it. A part of your gravitational force was used as centripetal force. Okay, your gravitational force was 24.6. Your centripetal force was 0.0842. Okay, so not all your gravitational force has been used up as centripetal force, only a portion of it. That's why here I say a part of your gravitational force was used as centripetal force. Okay, this is number one. So the balance of the gravitational force, the balance of the gravitational force is the resultant downward force measured by the Newton meter. So here your answer would really just be the reading equals to gravitational force minus centripetal force, 24.6 minus 0.0842, giving you the final answer of 24.5 Newton. Okay. Okay, so if you now look at the next page, in this question here, they mentioned that you have a satellite that's orbiting the Earth. For an astronaut in the satellite, his sensation of weight is caused by the contact force from his surrounding. So the astronaut reports that he is weightless despite being in the Earth's gravitational field. So state what is meant, or rather suggest what is meant by the astronaut reporting that he is actually weightless. So this one has something to do with your elevator problem in dynamics of AS. Let me just re-explain the thing a little for you. So I have one case, two case, and then three case here, the third case here. Okay. So this is your elevator problem from your AS dynamics. So say in your elevator right now, I have one person standing inside and the elevator is moving. Okay. So say for example, this first elevator here is moving upwards with a certain acceleration of A. And then the second elevator here is moving downwards with also a certain acceleration of A. Okay. And then the third one here is also still moving downwards, but the acceleration is equals to, say, the gravitational acceleration. So what we're interested to find out here is the weight felt by the person inside the elevator itself. When you're talking about the person inside the elevator, let's just consider the forces acting on the person. You have the weight acting downwards and then the reaction force acting outwards. Okay. So W down, R upwards. Like this. All right. So for the person that's standing inside the elevator, his sensation of weight comes from the reaction force from the ground to the person itself. So whatever weight you feel is actually due to this reaction force R here. Okay. So here, if I consider the first elevator here, if I apply the equation F net equals to MA, this one would actually be R minus W equals to MA. So that R is equals to W plus MA now. Okay. So how do I know which one is going to be positive or negative? In AS, you would have learned that when you want to apply equation F net equals to MA, any force that's in the direction of your acceleration will be positive. So like in your case, R is in the direction of your acceleration, so this one should be positive. Whereas any force opposite to your direction of acceleration will be negative. So W here will be negative. That's why here is R minus W equals to MA. Therefore, R is equals to W plus MA. So now what you can see from here is that your reaction force is the weight plus with MA. So here, what you could say is that your person will actually feel heavier than usual. So this one I would just say, therefore, the person feels heavier. Okay. How about the second case here, where you have the elevator moving down with a certain acceleration? So here you can use F net equals to MA. This time it will be W minus R, because W is in the same direction as your acceleration now, so it's positive, but R is opposite to your direction of acceleration, so it will be negative. This one is what you will get. So R here is actually W minus MA. So here you can see that it is your weight minus off with MA. Therefore, the person will feel lighter. Okay. So there's one thing here when it comes to the elevator problem in your AS. Now, there will be a very special case where you say that your object is moving downwards, but its acceleration is equal to G itself. So in such a case, what do you think would happen? If again you apply F net equals to MA, you will get W minus R equals to MA, such that R is equals to W minus MA. But now, if you expand out W is actually mg. And then if you recall that A is actually G here, MA is actually mg here. So eventually you get 0. So your reaction force from the ground on the person is actually 0. So under this specific case here, you will say that therefore the person feels weightless. Okay, and this is the condition where you can feel weightlessness. It's the same thing for the case where you have a person inside a satellite right now. Okay, so in your case, let's just assume that the Earth is here. For example, let me draw a sphere here to represent the Earth. And then you have a satellite right over here that's orbiting around the Earth. So you have a satellite here, and you have a person standing inside the satellite. So by right, there is the pull of gravity acting on that person, trying to pull him towards the Earth. This is your gravitational force. So as the person is being pulled towards the Earth, he will actually push against the floor of your satellite, thereby causing a reaction force acting up on the person. So you have R here. Okay. So now what you want to do is to look at what happens to this R. This R is what causes your sensation of weight. That one is already mentioned by your question right over here. His sensation of weight is caused by the contact force from his surrounding. It's actually referring to this R here. Okay. So if you're considering between the center of the Earth to the satellite orbit itself, this one is your R. Let's just call this R2. I want you to compare it with a different separation. Let's just say that you want to compare it with a person that is standing on the surface of the Earth. This one is probably your R1. Okay. This one is your R1. Okay. Now, we know that gravitational force is Gmm over R squared. Now, if everything else remains the same, you could actually say that gravitational force is inversely proportional to separation squared, such that if R increases, your gravitational force will drop. Okay, this is number one. And then the other thing you want to consider now is number two, the centripetal force. Centripetal force is actually mr omega squared. So here, if everything else remains constant, Fg would be proportional to R. Okay, the bigger your radius, the bigger your centripetal force. That's what you can see from here. Okay, so if your R increases, your gravitational force, sorry, your centripetal force would increase. Okay, so let's consider this now. When your person is standing right over here, it could be a case where his gravitational force is, say, maybe 10 Newton, but his centripetal force required for him to move in a circle like this around the equator is maybe just 1 Newton. All right, here you will see that there is a resultant downward force. Similar in concept to the previous question that you have done here, the one where they ask you to find the reading on the Newton meter. So here, your case is that your gravitational force is much larger than your centripetal force. There's actually some sort of balance remaining that gives you your resultant downward force. But what happens when you go further up? If you're going further away from the center, let's say you go from here all the way to here, what you could say is that your radius is increasing. So what this causes is that your gravitational force will start to drop, but your centripetal force will start to increase because of these two relations that you have deduced right over here. When your R increases, your gravitational force will drop, so that your centripetal force increases. So now when you go further up, all the way to where your satellite is, you could end up with a case like this, where your gravitational force drops down to 5 Newton, and then your centripetal force increases to 5 Newton. So in such a case, what you can see is that your Fg is equals to your Fc. There is no resultant downward force. This one, you will see Fg is equals to Fc. So there is no resultant downward force. Therefore, no contact force also. All right. But the case below here just now, where you have the person standing on the surface of the Earth, this one here, I forgot to write this. This one here is where your Fg is more than Fc, so there's a resultant downward force. But for the one above, Fg is equals to Fc, there's no resultant downward force because all your gravitational force has been used as your centripetal force. There's no resultant downward force. There by right should not be any contact force. So this one means that your R is 0. Okay, that would explain why your person standing on the satellite actually feels weightless. Okay, so if you now look at the answer that is written here, it will probably make more sense now. The first statement here says that the gravitational force provides the centripetal force for the astronaut orbiting the Earth. He is moving in a circle like this, so he must have centripetal force. This must be provided for by your gravitational force. Okay, and now specifically when the person is in satellite orbit, that gravitational force is actually equal to your centripetal force. Okay, so there's no resultant downward force. Your contact force is 0. But the way that the marking scheme wrote it is that they wrote it in a different way. They say that the contact force, which is the difference between Fg and Fc, is 0. It's actually kind of like the same thing that I wrote here, like where I said no contact force, but they write it here as contact force being the difference between Fg and Fc is 0. Thus, the astronaut feels weightless. Okay, now the contact force here being 0, you can actually say that the contact force is actually Fg minus Fc too. Because you see, I want to find out the resultant downward force. The resultant downward force, F net, should by right be Fg minus Fc, which in my case, I already know is 0 because Fg is equals to Fc. They are equal magnitude, so if you minus them off, you're going to get 0. That's why here the answer in the marking scheme wrote it as this. Your contact force, which is the difference between Fg and Fc, is 0, so your astronaut feels weightless. You are trying to basically explain why contact force is 0 here. If you're able to explain that, that will explain why your astronaut actually feels weightless. Now, in a lot of your gravitational field questions that you have done so far, notice that for those questions, you had always said that Fg is equals to Fc in order to do your questions. If you refer back to all the questions you've done so far, the part where we tell you Fg is equals to Fc is valid when an object is orbiting around another object at a very large distance. At a very large distance. Meaning to say it should be something like this. Okay. If you have a very large if you have an object that is orbiting around another object at very large distance, normally you can say Fg is equals to Fc. All right. This situation here kind of describes to you why. Because the further you go away, the bigger your centripetal force, but the smaller your gravitational force. You will come to a point where gravitational force is equals to centripetal force. Okay. But if let's just say you have the two objects and their separation isn't very large, you would have a case where FG is actually more than FC, like this one here. Like your current question here, you notice that you had a person or rock that's landing on the surface of the earth, and then that person or rock is moving in circular orbit. You cannot just simply say FG is equals to FC here, because here your FG is more than your FC. Okay, you can only say FG is equals to FC when very large distances are involved. So hopefully that is clear. Just have a look at page 20. Okay. Now, this is just 17P41. Just 17P41. Let me just open it up. Now, explain how a satellite can be in circular orbit around a planet. How is it possible that a satellite can move in a circular orbit around a planet in the first place? Okay, so this one is your planet. This one is, say, your satellite. How is it possible that a satellite can move in circular orbit about the planet in the first place? So this one relates to what I mentioned to you many times before, because you have gravitational force between your satellite and your planet. That gravitational force acts as your centripetal force, right? So if you want to explain, you just make mention of this, no? The gravitational force or attraction between your satellite and planet provides the centripetal force on the satellite about the planet so that it can move in a circle. So that it can move in a circle. Okay, so that it can move in circular motion. I think that's the better term. Okay. All right. Centripetal force, gravitational force between satellite and planet provides the centripetal force so that the satellite can move in circular motion. Okay. Oh yeah, another thing I probably should mention to you is this. Sometimes when you see in my written answers, you will see certain phrases that are in round bracket, like this one here, as well as this one here. Now, the statements in round bracket are statements that don't carry mark. Okay, I'm following what the marking scheme wrote. Generally speaking, if you look inside your marking scheme, you will notice that certain statements are underlined for some cases, and certain statements are in round bracket. The ones that are in round bracket has no mark. It's not important. Even if you did not write them in your answers, it's fine because it carries no marks in the first place. The examiners don't bother about that. You don't show it, it's fine. You show it, it's fine. Okay. But if you see a statement that is or term that has an underline to it, that one is actually important. Okay. It carries marks. Okay, it carries mark. All right. So just so you know. Okay, now if you move to the next part of your question, they tell you the Earth and Moon may be considered to be uniform spheres that are isolated in space. Earth has radius r and mean density rho. The Moon, small m, the Moon mass small m is in circular orbit about the Earth with radius nr as illustrated. Okay, Earth and Moon are considered to be uniform spheres here. All right. Now, the next part of the question mentions this. The Moon makes one complete orbit of the Earth in time t. Show that the mean density rho of the Earth is given by this expression where rho is 3 pi n cubed over gt squared. Okay, now for this particular question, it's kind of related to your Kepler's third law also. All right. Because you see, I mentioned to you last week, if you see your equation, whatever it is, has a square term and a cube term, it almost always will relate to Kepler's third law, because Kepler's third law is the only equation in this chapter that has a square and a cube. Okay, so this one, you know, you're definitely going to do something related to Kepler's third law. Okay, so when you derive Kepler's third law, you always remember that gravitational force provides your centripetal force, and the other day you do your derivation, right? There's some stuff here that you need to be careful of when you try to do your derivation. Now, in the first place, Fg was gmm over r squared. Fc is mr omega squared. All right. Now, if you try to relate to your question here, the variables that are defined, you need to adapt it to the general equation. All right. Now, in your case, you see what is the center to center distance between the masses. You see, when you're talking about R, this one is center to center distance between the masses. All right, yeah, R can mean radius now, all right, but specifically it's actually center to center distance between masses. So if your moon is this one, okay, your center to center distance is from this point to this point, which is NR. So your R here, if you go and modify, if you go and adapt it to follow what your question is describing, this is supposed to be NR. Okay. So this is what you're supposed to substitute for your R in your general equation. Okay. And then another thing that I should probably mention is also the FC. FC is mr omega squared. You see R is somewhat radius also, right? For most of the time when you look at this one, it won't necessarily be center to center distance between masses in one of the questions that you see. When we talk about Fc equals to mr omega squared, this is actually the distance between mass to center of rotation. Okay. There's a difference between the R for Fg and the R for Fc. Although they seem the same, they can mean different things. Okay. So for Fg, it is center to center distance between the masses. For Fc is the distance between mass to center of rotation. Okay, distance between mass and center of rotation. Sorry, not to center of rotation. Okay, now in your case here, this one is okay lah, because you see, your moon is moving in a circle like this. Your center rotation is also the center of mass for the Earth. Okay, is the center of rotation is right at the center of the other mass that you're talking about. Okay, so this one no issues. This one will also be NR. Okay, this R here will be NR also. Okay, so just bear that in mind. All right, so if you already get that, you see here Fg is Fc gmm over nr square, then you get mnr omega square. Eventually you get gm equals to nr cube omega square. From here, you just really want to get rid of the omega, where you just sub in omega equals to 2 pi over t. So on the right hand side, you get nr cube 2 pi over t squared. Now on the left hand side, you need to sub out something, because you see in your current equation here, you notice that you actually have an expression for density inside. This original form does not have density. You need to change out something so that you have an expression for density inside. Okay. The hint would come from the fact that you don't see a big M inside. You see, in your Kepler's third law, you're supposed to have a big M, which was the main mass. So somehow or another, this equation does not have the big mass anymore. It has somehow disappeared, and then suddenly in its place, you have a expression, you have density. You have one term for density. So the hint could be that you go and sub out M so that it has something to do with density. So the easiest thing to relate to is density is mass per unit volume, where mass is density times volume. And since this is a sphere, it's going to be pi r 4/3 pi r cubed. Okay, they already told you that the radius of your Earth is r. They already told you here, right? Okay, so you can just use 4/3 pi r cubed. There's no need to multiply with n or whatever. Okay, so eventually you get 4/3 pi r cubed rho. Okay, so you sub in for m over here, multiply with g, then you get this expression. Then from there, all you just need to do is you try to simplify whatever you see here. Eventually you get 3 pi n cubed over gt squared. That one would be for this question. Okay. Yeah, this is as complicated as it gets now when it comes to Kepler's third law. You need to play around with the variables. All right, so if you look at the next page, they tell you that the radius r of the Earth is 6.38 times 10 power 3 kilometer, and the distance between the center of the Earth and the center of the Moon is 3.84 times 10 power 5 kilometer. The period T of the orbit of the Moon about the Earth is 27.3 days. Use the expression in B that you have to calculate rho. So the expression in B just now was this one. Rho is 3 pi n cubed over gt squared. Use this expression to calculate rho. All right. Now from here, you try to see first, do you have everything? You have the universal constant, the universal gravitational constant g. You have the period at 27.3 days, but you don't seem to have n though. Okay, so you cannot just straight away use this. You need to find out what was n. So it so happens that they already gave you one particular information. They told you that the distance between the center of the Earth to the center of the Moon is 3.84 times 10 power 5. So it's just now this one was your planet, and then this one was your moon. It's Earth lah. Sorry, this one was your Earth, and then your moon. Wait, why did I submit? This one was your Earth, and this one was your moon. This one was NR. Okay, if you look back at the previous page, distance between the center to moon, center distance is NR. It is now 3.84 times 10 power 5 kilometer. Okay, so you can just say that NR is 3.84 times 10 power 5 kilometer. Remember to change it to meter. That's the reason why you have a 10 power 3 there. And then after that, you sub in the radius of the Earth. They already told you the radius of the Earth, capital R, is this value. So sub in also 6.3 times 10 power 3, again change to meter. Then eventually you will get N as 60.19. Okay. So once you have N, you can now proceed with this one. Okay. Then you will get your answers already. Rho is 3 pi 60.19 cubed divided by 6.67 times 10 power minus 11 and 27.3 times 24 times 3,600 squared. Days, you need to remember to change to seconds. You multiply with 24 hours multiply with 3,600 seconds. So eventually your density will be 5.54 times 10 power 3 kg per meter cube. Okay, so far so good with this. All right. Okay, page 13 is on June 16 P42. So let me just get that out. Okay, June 16 P42. All right, so if you read the question, they tell you right now for this question, you have a binary star that consists of two stars, A and B, that orbit one another, as illustrated in figure 1.1 below. The stars are in circular orbit with the centers of both orbits at point P, a distance d from the center of star A. Now, explain why the centripetal force acting on both stars actually have the same magnitude. Okay. Now, you see, a lot of the examples you've done so far was something like this, where we tell you you have a mass here right at the center, and then after that, you have another smaller mass that is orbiting around the bigger mass. Okay, this is the common case that you were looking at most of the time up to now. This current question is not the same as what you've always been doing. This one, you notice that there's star A and B. Both stars are actually moving. Both objects are actually moving in a circle. In the cases that you have always seen, the center mass was always stationary. Only this one was moving. Okay. But the current one that you have, you again have two different objects, but both objects are actually moving in a circle. You don't have one of the masses actually being stationary. So to illustrate what I actually mean by that is that, you see, you have a star A and star B, right? One part they tell you you have star A is moving in a circle about point P. Okay. You also have another star. That one is star B. I shouldn't use green. That one is star B. But it's also moving in a circle. Okay. The center of rotation is over here. All right. A, you see, is moving like this. A, you see, is moving like this. B, you see, is moving like this also. Okay. They're both moving in a circle. All right. And your center rotation is just some point in space. Okay. If you compare with the cases that you've always done, one of the masses was not moving, and for the mass that wasn't moving, your center of rotation is the stationary mass itself. Okay. But this current question is modified a little. Your center of rotation, you don't have a stationary mass. Your center of rotation is not on the mass itself. It's some point in space. Okay, that's the one thing that I need to highlight to you right now. Okay, so here the question is asking you, explain why is it that the centripetal force for both stars actually have the same magnitude. Now, in the first place, you see, for star A and star B, they will exert gravitational force of attraction on each other. So if we say that star A has, because star A and star B have both have masses, they will exert gravitational forces of attraction on each other. So the Fg on A would be the same as Fg on B. Okay, and we know that gravitational force is the one that provides us our centripetal force, right? So here I can say that Fg for A provides me my centripetal force for A to move in a circle. Fg for B provides me my centripetal force for B to move in a circle. But since the forces are same in the first place, the centripetal force must be the same, no? Okay, so let me just reiterate the statement. You see, by Newton's third law, the stars will experience equal but opposite gravitational force. As your gravitational force is the one providing your centripetal force, both stars will therefore have same magnitude of centripetal force. Okay, this one, some people when they just read this, I don't know, somehow they got confused. That if you want another different explanation and you want to see it in the form of an equation, it's possible. You just look at the statement on the corner here. Again, this one was updated quite recently, I think last year. Now you can just think of it as this now. Gravitational force on star A is the centripetal force on star A. Gravitational force on star B is the centripetal force on star B. Okay, but since gravitational force on A is the same as gravitational force on B because of Newton's third law, therefore centripetal force on A is the same as centripetal force on B. Okay, this one is in equation form now, but written in sentence form is this. Okay, this is the explanation for it. All right, so far so good, I hope. All right, so this one I think takes some time to digest. Okay, now this is where it gets more complicated in terms of calculation. So let's look at the first part first. Okay, first part is still okay. They tell you the period of orbit of the stars about point P is 4 years. Okay, both stars A and B have a period of 4 years about point P. Now calculate the angular speed omega of the stars. Now this one will be pretty straightforward since you already know the period. You can actually just find out omega from omega equals to 2 pi over t. All right, so it will be 4 equals to 4 years multiplied with 365 days, multiplied with 24 hours, multiplied with 60 minutes and 60 seconds, giving you 4.98 times 10 power minus 8 radians. Okay. All right. Now, another thing I should probably mention to you is this, because some people, now in general, 1 year is 365 days. This is the correct one. This is the value that your exam answers are always based on. Okay. Some people use a different value for days for 1 year because their understanding was, maybe I use a different color. For some people, their understanding was 1 year has 12 months. And then in a month, you have on average 30 days. So if you take 12 times 30, you're getting 360 days. That is how some people got 360 days. Now, when you want to convert from years to days, do not ever use 360 days. This one is never accepted by your exam. Okay, 1 year to them is not 360 days. 1 year to them is 365 days. So if let's say you had used this as 360 days, you will be marked as wrong. It is strictly speaking 365 days. Okay. So eventually your omega is 4.9 times 10 power minus 8 radians per second. Just remember this is the answer. All right. Okay, then after that, we move on to the next one. And this is the confusing part. All right, so if you look at part B, they tell you the separation of the centers of the stars is 2.8 times 10 power 8 kilometers. The mass of star A is MA and the mass of star B is MB. The ratio of MA to MB is 3. And then now determine the distance D. Okay, they ask you to determine distance D right now. What was distance D in the first place? If you look at your diagram, distance D is this one. Okay, wait on. Distance D is this one. Okay, that is distance D. And the separation between the stars is 2.8 times 10 power 8 kilometer. They told you distance D is this one. Okay, distance D is this. This is distance D. But they also give you the distance between your stars. That one was 2.8 times 10 power 5 kilometer. Okay, right? So now you try to make use of the information that you have before this. You see, before this, they ask you to explain why the centripetal force for both stars A and star B's are the same. So you make use of that information that they ask you to explain. You say that, okay, centripetal force of A is equal to centripetal force of B. Then after that, you try to expand out the equation and try to relate it to D. Okay. So in your case, if you're talking about centripetal force of A equals to centripetal force of B, yeah, we know that centripetal force is mr omega squared. But now, you see this R, remember I mentioned to you, is distance between mass and center of rotation. In your case, your FC, sorry, the centripetal force for A will be this, okay? Mass of A multiplied with distance D. You see, distance D is actually the distance between mass A and the center of rotation. Okay, here I wrote it as MARA omega square A omega A square. If I rearrange this one is MD omega square. Okay, if I'm talking about the centripetal force of B, it should be MBRB omega, MBRB omega B square, right? Okay, now B RB would be this one. Okay, yeah, maybe I write this one. This one is my RA. This one will be my RB, which ought to be 2.8 times 10 power 8 minus D, then times omega squared. Now, why do I use the same value of omega for both? Here I wrote omega A and omega B, right? But then suddenly here I wrote both omega, right? Is because, you see, omega is 2 pi over T, right? Remember just now they told you that your period of orbit for the stars, for both stars are the same. Both stars have a period of orbit of 4 years. If you look at omega equals to 2 pi over T, same T means same omega, right? So this one is one thing to know now. So same T means same omega. That's why here I replace omega A and omega B as just omega because they are the same thing. Okay, so that's how I got this little expression here. All right. Then from there, you can try to solve. Okay. You eventually get MAD equals to MB times 2.8 times 10 power 8 D. Then after that, you make use of the information that they gave you. They told you the ratio of MA to MB is 3, right? So you try to shift MB to the other side. Eventually, you will get MBD equals to 2.8 times 10 power 8 minus D. And then after that, you try to simplify it even further. You get 3D equals to 2.8 times 10 power 8 minus D. Eventually, D will be 10.7 kilometer. Okay, right. Sorry, this one I wrote it wrongly. This one is this part here I wrote it wrongly. This one is not 10.5 kilometer. This one is 10.8 kilometer. My mistake. Okay. Right. So this one, the distance is 2.8 times 10 power 8 kilometer. RB should have been 2.8 times 10 power 8 minus d in kilometer. Okay. Right. So I don't need to change the meter because I noticed that unit of A will cancel off unit of A, unit of omega will cancel off unit of omega. So whatever unit I have here will be the unit that I have here. Okay, so if I leave one of them in kilometer, the other one will be in kilometer also. There's no interference whatsoever. You can change it to meter lah, but you just make your life a lot more difficult lah, because afterwards you need to convert it back to kilometer. I mean, if you are careful, like looking at the equation, you will notice that mass unit will cancel off, omega unit will cancel off. So whatever unit of distance that you use will be the final answer, will be the unit of your final answer. Okay. Right. So this one should be okay, right? You just need to be careful a bit about all those little variables. Then I move on to the other one, the other question. Okay, so I'm going to go through this very slowly again. Now use your answers in A2 and B1. Basically use the answers from the previous two questions to determine mass MB or star A. Explain your working. All right. Now here I would actually use FG equals to FC because I know that star A moves in circular orbit. Star B also moves in circular orbit. FG would be equals to FC. Now, for my case here, I'm asked to find out for MB. But then you notice that how come I'm using FG equals to FC for A when they're asking me for B? Now, this is where if you look at FG equals to FC for A, if you apply equation Fg equals to gmm over r squared, remember I told you that the r is the center to center distance between the masses. In your case, the center to center distance between your masses, this one is actually this one. Okay, you're using the center to center distance between the mass. You're not using the distance between the mass to the center of rotation. Okay, so there's a difference here. This is the one point that I want to highlight for you guys when it comes to FC and FG. All right. R for FG is center to center distance between mass. R for FC is distance between mass and center of rotation. Okay. So in some cases, they are the same. Some cases, they are not, like in your current question. All right. So if let's say I want to say FG equals to gmm over r squared, it will be gma times mb divided by the distance between the masses squared. So this one, I need to change my kilometer to meter. 2.8 times 10 power 8 times 10 power 3, remember to square it. Okay. And then after that, my mr omega square will actually be mad omega squared. So this d is this one. This one is the distance between mass and center of rotation, which is this one. Okay, they're not the same distance. All right, because I heard people do this before where they say that, yeah, where they cancel off the r because they say, oh, gmm over r square is mr omega square. So this r will cancel off, then this square will cancel off, then giving me some value. Right, this was something that you have been doing all this while in all your previous questions, if you notice. But here, you do not do that, right? Because the r's are different, completely different. So just something to note, all right? Okay, so your centripetal force, your R, is your D, which you already found in the previous question. All right, so you make use of that. And then now your equation, you will get MB is 2.8 times 10 power 11 squared times dW squared over G. Now, the reason why I wanted to use A in the first place is because you notice that if I consider FG equals to FC for A, the MA will cancel off, leaving me only MB, which is what I want to find. This is the reason why I consider A only first, because I want to find B. All right. When you see MB here, the first thing that would occur to you is to probably use FGB equals to FCA, isn't it? But eventually you notice that the mass cancel off. Yeah, I'm going to end up with MA instead. Okay. So that's the reason why I use for A now, because I want to get B directly. So now you have this final equation. You just sub in everything. You get 2.8 times 10 power 11 square. Then your D, remember to change from kilometer to meter. Then multiply with your omega that you found from the previous part. Remember to square it. Then divide by your G. Eventually, you're going to get 2.04 times 10 power 9 kg. This is your answer. Okay, so this is one part. Okay, yeah, this one is as complicated as it gets. Right, there will be no other questions in your entire past year that is as complicated as this. This is by far the more complicated and confusing ones that have ever come out in your past years. The rest are pretty straightforward. Okay, so this one is all right. Oh yeah, let me just explain a little bit more before I end the lesson. Let's just say that if you had started off with gravitational force equals to centripetal force for B, because you wanted to find B, you can still proceed with it. There will be no problems, because you see, if I say that FGB is equals to FCB, where you say GMAMB is the same as whatever values you have there. Let's just say RB squared. Okay, maybe I just do this. When you say that's GMAMB, it's 2.8 times 10 power 8 times 10 power 3 squared, then equals to MB, yeah, equals to MB, then 2.8 times 10 power 11 minus D, then omega squared. Yes, you will get the same thing where MB cancel off, eventually giving you MA, the value of MA. But you can actually do something out of this value, because you see your question originally gave you the ratio of MA to MB. So if let's just say you had started with gravitational force equals to centripetal force for B, and then eventually you get mass of A, you could have actually turned it around by using this ratio that has been given to you. Okay, you can actually find out what is MA first, and then subsequently using the information that MA to MB is 3. So if you know MA, you'll be able to find out what is MB. Okay, so you could also do that if you wanted to. You can turn it around, but that one makes your calculation longer, all right? But you can still solve it, all right?